In this discussion, we're going to talk about orthogonal trajectories. And what we're going to do is we're going to use differential equations to find curves that run perpendicular to the curves we already know. And the ones we're finding are called the orthogonal trajectories of the first. Without a diagram, this doesn't really mean a whole lot. Oops, pardon me. As I've explained before, when I get over here to the side, it's hard to write. Okay, I'm sorry for that. Now, here's the idea. We're going to be given a family of curves. So we start out with a family of curves. Now, what's meant by a family of curves? For instance, y is equal to x squared plus arbitrary constant. And so the idea is for every particular constant, we have a particular curve. So as an example, if c were equal to 0, then we would be talking about the curve y is equal to x squared. On the other hand, if c is equal to 1, we would be talking about y is equal to x squared plus 1. Or if c was equal to negative 1, we would be talking about y is equal to x squared minus 1. Now, I've chosen these c values as integers, but there's nothing that says that they have to be integers. But let's just take a quick peek about this in this particular situation. What would this look like? Well, if this is where 1 is, and this is where 2 is, and this is where negative 1 and negative 2, of course, y equal x squared, roughly, and that's all I'm doing here, would be this curve, wouldn't it? On the other hand, y equal x squared plus 1, that's when c is 1, would have a curve that looked like this. And if we had c is equal to negative 1, y equal x squared minus 1 would be a curve that looked like this. So for every c value, we have a different curve in this family. And of course, you can imagine for all the possible c's, if we were to graph every single curve in the family, it would blacken the paper because it would be filled in completely and we couldn't see it. So the idea is we're going to be given a family of curves. Now what we're looking for is the orthogonal trajectory. So we're looking for a second family of curves. And this orthogonal, orthogonal really means perpendicular when we're talking about curves. Now, of course, when we're talking about straight lines, we understand perpendicular. But when we're talking about curves, we're looking at for instance, here is a curve, and at this point we'll say we have another curve that intersects here, okay? And at this intersection point, if we were to look at the two tangent lines, the tangent lines themselves would be perpendicular. So we talk about at that point the two curves are orthogonal, or the two curves are perpendicular at that point. So we're looking for a second family of curves, and when we pick one of the curves in that family, it will intersect every curve in the first family in a orthogonal or perpendicular way. So that's the first thing that we're looking for. So what I'd like to show you is an example of two families of curves that satisfy this condition. Okay, so let me pause here to bring up a graphic, and then I'll talk at that point about the graphic, and then we'll see about how we're going to deal with these.
Okay, now you notice here we've got a set of blue curves, and that's the y equal x squared plus c. And I've just put a few examples in there, like I said before. And then we look at the red curves. Now the red curves is a family of curves that's the orthogonal trajectory to the original curves, y equal x squared plus c. And so for instance, pick out one of these red curves. Well, actually it's a pair, and we don't really need to know what the equation of this curve is, but it's a pair of curves that go together. So follow along this one particular curve, and notice this curve intersects this parabola in a perpendicular way. It intersects this parabola in a perpendicular way. It intersects every one of these parabolas in a perpendicular way, here and here as well. And if we had any other of these parabolas, it would intersect those in a perpendicular way. You choose another one of these red curves. Remember, they are a pair here. And so, for instance, this red curve, this orthogonal trajectory, also intersects each one of the parabolas in an orthogonal way. I mean, for one thing, that's pretty cool, but that's the idea. We're going to be given one family, and we're to find the second family, which is called the orthogonal trajectory. Okay, well, let's get back to our video then.
So here's a pause.
My pause isn't in sync.
What's the practicality or what's the usefulness of these orthogonal trajectories before we find them? Well, as an engineer, you would see that they're used quite extensively when you're studying electrostatics, or they're used quite extensively in thermodynamics. Or they're used extensively in hydrodynamics. In fact, they're used in lots of different engineering fields, and they're very important in terms of modeling. Now, of course, it's above our pay scale at this point to understand how they will be used in those different areas. What we're going to do is look at a simple example of how we can actually find the orthogonal trajectory of a particular family of curves. What's the process that we would take? But let me kind of say something about this modeling to make it seem a little more real. Now, that's not what we're going to actually work on, but let me give you an example of how that might be used. Okay, so let's imagine that we have say a new car model. And in order to describe the surface, you are measuring the distance between a reference point and the model surface. And let's say we're using something like sonar to do that. And let's assume that we're doing this for several heights, let's say in intervals of 1 centimeter. That's what that should be. That doesn't look like a 1 centimeter, but that's what I mean. Now, after doing this, the result will be a number of curves, we'll say, that kind of go from front to back along the car. Okay, so we'll have the surface kind of described, if you will, as maybe a layer of like onion rings. Okay, so a thin layer of onion rings is how now I hope you can imagine this. Oops, onion rings are describing the surface. But we want to go from, so think of all these curves, like I said, they're kind of running from front to back along the car. But we need to take this information and create a wireframe model to get something that looks a little, a wire type representation. So we need curves that, if you will, go from top to bottom or bottom to top, so they go in a vertical fashion rather than a horizontal fashion. And each one of those curves, of course, has got to represent the original onion rings, differential equations, to find the orthogonal trajectories of the onion rings. That is, the second set of curves that describe the model vertically. Oops, I didn't spell correctly. Orthogonal trajectories. So that gives you some idea of something that we can kind of understand on how we might apply this. Well, let's actually put our solving differential equations to practice and see how we would do it in a particular case. Okay, here's our problem. We're to find I keep having trouble here. Let's see, orthogonal Find the orthogonal trajectories for the family of curves given by y equals c over x, where of course c is an arbitrary constant. So we have a whole family of these curves. Now, here's the plan. We need a second family that is perpendicular to any member of this family. Now, so that means at any point that we choose on a particular curve, we're looking for another curve that intersects there in a perpendicular way. That would be the a relationship that the two tangent lines at that point have to be perpendicular. And the way we find slopes of tangent lines is via the derivative. So let me do this in this particular case. Let's isolate the constant c because it's causing us a little bit of grief here. So step one for us here is to isolate c. And all I'm doing is multiplying both sides of the equation by x. So we get yx is equal to c. Now, maybe it's not clear why I'm doing this at this point. But the next thing we're going to do is we're going to find the derivative of both sides with respect to x. So we're finding the derivative with respect to x of the left side and the derivative with respect to x of the right side. Now, the purpose that serves, of course, is on the right side we simply get 0. And on the left side, we have to use the product law or and implicit differentiation together. So in this particular case, and maybe I should have written that as x times y rather than y times x, but the result we'll get on the left side will be x times y prime plus y. Okay, so now let's solve this for y prime. I mean, basically we have a differential equation now, don't we? And there's no arbitrary constant in this differential equation, which is kind of important to us.
Let me pause right here because I think I haven't made this clear. This isn't the only way to have done this, that we didn't have to solve for c first. But because we solved for c, then the differential equation that we get here does not depend on the arbitrary constant c. So we don't want to find a single curve that goes with a particular c value. And that's the reason we would like a differential equation that does not have a constant, an arbitrary constant in it. Now, later on, if we wouldn't have solved for c originally, and we would have found the derivative just from what our original equation, y equals c over x, which we could do, then at a later time, we would have c in there, and we would still want to replace every place we saw c with x times y or y times x, and that's another way we could accomplish eliminating the arbitrary constant c, which is important when we're doing these.
But we can certainly solve this for y prime, and we'll subtract y on both sides and then divide by x. So we get y prime is negative y divided by x. Okay, so at any given point, x comma y, then this tells us the slope of the curve that goes through that point. The general point, x comma y. So in other words, that's the slope of the family. That's the formula for the slope of the family. The slope of the family. Now, here's the big thing. We know to be orthogonal, that is, we know to be perpendicular, perpendicular slopes, or perpendicular lines, I'm going to say perpendicular slopes, are negative reciprocals of each other. In other words, if you have a line that has a slope of 1/2, to have a line that is perpendicular to it, it must have a slope that is the negative of the reciprocal of 1/2. Well, of course, the reciprocal of 1/2 is 2, and so we would have to have a line with a slope of -2 to be able to have a perpendicular line. And so what we need for perpendicular, so the slope of the orthogonal family must be the negative reciprocal of the slope of the original family, which is negative y over x. Well, that negative reciprocal then is actually positive x over y. X over y is the reciprocal, and of course under the opposite of, so y prime equal x over y is the slope of the orthogonal family. Okay, so what we want to know...
Let me pause again right here. We know the slope of the orthogonal family has to be the negative reciprocal, which is x over y. And so that being the slope, that's why we know y prime is that x over y. Okay, let's continue.
Is what describes what are these particular functions. Well, we have a differential equation to solve, and it's that simple. And in this case, we can solve by separation of variables. So we write y prime, of course, as dy over dx, and it's equal to x over y. And as we separate the variables, then we end up with y dy is equal to x dx. Now, as we integrate both sides, then we end up with 1/2 y squared is equal to 1/2 x squared plus our constant integration that we've gathered to one side. Now, what we could do at this point, well, we could do several things, but what we could do at this point is we could multiply through this equation by 2. And when we do, we would get a y squared is equal to x squared. And of course, 2 times a arbitrary constant is just an arbitrary constant. So rather than saying 2c, I'm just going to say c, the arbitrary constant. Now, I could write this a little differently by subtracting x squared on both sides. And so that I would have y squared minus x squared is equal to c. And then you might recognize this, and I hope that you would, that this is really the equation of hyperbola, isn't it? And so I'm going to make it look a little more familiar, just taking another step, and I'm going to divide through by this arbitrary constant c. And when I divide through by c, I get y squared over c minus x squared over c, that's the same c, is equal to 1. And I didn't really have to do that. I could have left it as below. But the family of curves given by this formula, where c is the same as for both of those denominators, every one of the curves, for instance, y squared over 2 minus x squared over 2 equal 1, will be orthogonal to every one of the curves above y equals c over x, no matter what c we choose there. Y equal 1 over x, y equal 2 over x, y equal negative 3 over x. This curve will be orthogonal to every one of these curves, every one of the family here. In fact, let me pause here and bring up kind of a diagram, if you will, of these two families.
Yeah, you can see here I'm trying to get it into this picture so that we can see them. Now, what's important here to understand is our original family of curves was y equals c over x. Now, y equals c over x, when c is positive, like y equal 1 over x, well, it's going to be a rational function that has 2 branches. And here would be one of the branches, and over here would be the corresponding branch. Now, if the c's of that original family were negatives, like c is negative 1, we would have y is equal to negative 1 over x. And so it would be also a rational function that would have 2 branches, but they would be paired left to right, upper left with lower right. So it's a pair of curves that one curve consists of a pair of branches in either of these cases. But you see that as here's some examples of the original functions, or what the graphs would look like in the family of the original functions. Now, what we got was the orthogonal trajectories was basically a family of hyperbolas. Now, if the constant c was a positive, then the hyperbolas are opening vertically, up and down. So here would be for positive c's. If the c's were negative, we'd actually have x squared over some number minus y squared over some number equal 1. And then our hyperbolas are opening horizontally on the left and on the right. So I've just put a few examples of those. But regardless, if you take any one branch of any one of the curves and you follow it through, you'll notice, for instance, this curve is orthogonal, this red curve is orthogonal or perpendicular to every one of those blue curves. Isn't that cool? It still amazes me. Likewise, we pick one of these curves up here and follow it through, it's perpendicular to every one of the blue curves, even if we expand this. So that's the idea of orthogonal trajectories, or at least how we proceed to find them. And of course, there's a lot more that you would learn in a differential equations course, but this gets us started. Signing off in this section.